Today we'll be explaining how the respiratory chain in the mitochondria works. So here you have your typical eukaryotic cell, and we're going to be focusing solely on the mitochondria. So here you have your intermembrane space, your matrix, your outer membrane, but most importantly your inner membrane. And this is where the respiratory chain is located and where all of these reactions are going to take place. So complex 1 acts as a proton pump and will pump out 4 protons when electrons pass through. Here you have complex 2, which is the same enzyme that acts in the Krebs cycle. And it's important to note that this is not a proton pump, and that's going to be really important later. Here you've got complex 3, which is very large and pretty complex. It has 11 subunits and is bigger than all of the rest. And then here you've got cytochrome C, which acts as a vectorial transporter for electrons. Here in green, you've got complex 4, and this is the last complex where the reduction of oxygen into water is going to occur. And here you've got ATP synthase, and it's going to produce ATP from ADP and phosphate thanks to the energy gradient produced by the respiratory chain.
In complex 1, electrons enter in pairs from different sources. We're going to focus on NADH. NADH is oxidized into NAD+, so 2 electrons are transferred through FMN and iron sulfur centers up to Q. And Q is a mobile transporter and can accept 2 electrons and 2 protons. This then results in QH2, which is also known as ubiquinone. The oxidative process will release the energy, which will allow 4 protons to be pumped from the matrix to the intermembrane space. Following with complex 2, at the same time that NADH is being oxidized into NAD+, in complex 2, succinate donates 2 electrons to FAD, which results in FADH2. And these electrons then follow the same path as in complex 1 through the iron sulfur centers up to Q. And Q accepts again the 2 electrons and is once again transformed into QH2. But importantly to note, complex 2 does not pump protons into the intermembrane space. The series of reactions of complex 1 and 2 will contribute to the pool of reduced ubiquinone, also known as QH2.
Complex 3. This large complex couples the transfer of 2 electrons from 2 QH molecules to cytochrome C. At the same time, we have the vectorial transport of 4 protons from the matrix to the intermembrane space. Cytochrome C, a mobile transporter which can only carry electrons one at a time over to oxygen, located in complex 4. So the oxygen can be reduced into water. Complex 4. One cytochrome C donates its electrons to this complex. 2 electrons, equivalent to 2 cytochrome Cs, are used to reduce 1/2 molecule of oxygen into 1 water molecule. Because we have 4 electrons donated in normal conditions, reduction results in 2 water molecules. Finally, 2 protons are consumed from the matrix and pumped to the intermembrane space.
So the final result of the activity of all these complexes is that we have a high proton concentration into the intermembrane space. It creates a gradient that allows the passive diffusion of protons through the ATP synthase, and that allows the generation of ATP. Energetically speaking, the value of this reduction potential is what allows the respiratory chain to function. So now we're going to use this reduction potential diagram, and we're going to make a recap of what we just saw in the membrane, but this time in this diagram. So on the left side, we have the value of the reduction potential of every couple. We have this one, which is NADH, NAD2 reduction potential, and this one corresponds to O2 and H2O. Electrons are going to be transformed from lower reduction potential carriers to higher reduction potential carriers. In complex 1, we're going to have the couple NADH, NAD+. Its oxidation is going to release electron to ubiquinone. This reaction is exergonic, so it releases energy that allows the pumping of H+ through the membrane. In the complex 2, the oxidation of succinate in fumarates is going to also release electrons, but this time the reduction potential is really close to 0, so it doesn't allow the energy production. Then these electrons are going to come from ubiquinone to the cytochrome C in the complex 3, Once again, direction is exergonic, so we have the pumping of electrons. Then from cytochrome C, it's going to go to the complex 4, and then from the complex 4, it's going to come to O2, and then we're going to have, thanks to this electron, the production of H2O. This reaction, once again, is exergonic, so it allows the pumping of H+ through the membrane. So if we want to make it more simple, it's like electrons are at the top of an energy hill. They go down the hill, and while they do that, the reduction potential increases. They go from one transporter to another, and while they do that, their reaction releases energy. Thank you for your attention, and I hope it will help you understand.